a hairline crack opens in a wall. In modern concrete, that can be the first quiet step toward corrosion, leaks, and expensive repairs. But inside some ancient Roman material, a crack may trigger something stranger. Water enters. A pale mineral fragment reacts. New stone begins growing into the gap. That sounds like a legend designed for a viral video, except researchers watched a Roman-inspired version happen in the laboratory. The trail begins with buildings that have already survived nearly 2,000 years and with a feature so ordinary that generations of experts treated it as a mistake. Those white chunks inside Roman concrete were hiding in plain sight. Roman concrete has earned its reputation honestly. The Pantheon, dedicated in 128 CE, still carries the world's largest unreinforced concrete dome. Remains of aqueducts, ports, sewers, and seawalls have endured weather, water, and earthquakes for centuries. But there was never one magical Roman recipe. Builders changed aggregates, volcanic materials, lime, and methods depending on location and purpose. A harbor exposed to seawater is not chemically identical to a wall built inland. So the real question is not, what single ingredient made Roman concrete immortal? It is, which combinations of materials and manufacturing choices created unusual durability? And can any of those mechanisms be reproduced today? One investigation focused on mortar from a roughly 2,000-year-old city wall at Privernum, south of Rome. Under a microscope, the material contained bright millimeter-scale pieces called limeclasts. These pale fragments are common enough in Roman concretes that researchers had known about them for years. The easy explanation was poor quality control. Perhaps the lime had been burned badly, slaked incompletely, or mixed carelessly. In other words, the Romans made excellent concrete despite these lumps. But that explanation bothered the research team. Why would builders who refined their materials over centuries consistently leave the same obvious flaw? What if the supposed defect was part of the design? To find out, the team mapped the clasts at several scales using electron microscopy, elemental analysis, X-ray diffraction, and Raman imaging. The chemistry pointed toward a hotter process than the standard story allowed. Lime was usually imagined as being slaked first, quicklime mixed with water to create a paste, then added to the mortar. But the clasts contained structures consistent with quicklime being added directly, either alongside slaked lime or instead of it. When quicklime meets water, the reaction releases heat. This hot mixing process changes the chemistry, accelerates reactions, and leaves calcium-rich clasts with a brittle, porous internal structure sealed inside the hardened material. That brittle structure matters when damage begins. A small crack moving through the mortar tends to travel toward and through a lime clast. The clast fractures, exposing a large reactive surface. Then water arrives. Calcium from the clast dissolves into the water, creating a calcium-rich solution that can move into the crack. As conditions change, calcium carbonate precipitates from that solution, forming solid mineral material inside the opening. Calcium can also react with the surrounding volcanic components and strengthen the cementing matrix. The remarkable part is the sequence. The crack exposes the reservoir, and the water that threatens the structure also activates part of the repair. A plausible mechanism is not enough. The team built modern concrete analogs containing quicklime, cured them, split the samples, and held the crack walls about 0.5 millimeter apart. Then, they ran water through the openings. In the reported tests, cracks in the hot mixed material filled within 2 weeks, until water could no longer flow through. An otherwise comparable sample made without quicklime stayed open, and the water kept running. The experiment did not prove that every ancient wall heals every fracture. It showed that lime-clast chemistry can produce measurable self-sealing behavior under controlled conditions, matching mineral-filled cracks seen in ancient samples. This is where the headline needs guardrails. Self-healing does not mean a shattered column rebuilds itself. The laboratory cracks were around 0.5 millimeter wide. The process needs the right material, reactive clasts, water, and chemical conditions. Roman formulations also varied across centuries and environments. Marine concretes can develop other long-term mineral reactions involving seawater and volcanic material. The Privernum study examined an open-air wall. Even the word concrete can blur differences between ancient mortar and modern reinforced structural concrete. The evidence is exciting precisely because it is specific. Turning it into a universal superpower would make the story less accurate, not more impressive. Why should modern engineers care about an ancient mortar trick? Because durability changes the lifetime cost of construction. Cement production requires enormous heat and releases carbon dioxide both from fuel and from the chemical conversion of limestone. A formulation that keeps a bridge, tunnel, or building useful longer could reduce repairs, demolition, replacement material, and disruption. But ancient inspiration is not a free environmental pass. A modern mixture still needs testing for strength, reinforcement compatibility, freeze-thaw cycles, salts, construction speed, cost, and emissions. The useful goal is not to copy Rome word for word. It is to isolate a mechanism, measure it, and adapt it responsibly. The discovery also changes how we interpret old technology. Archaeological materials rarely arrive with complete instructions. Researchers reconstruct a process from mineral phases, reaction rims, pores, historical texts, and experiments. The lime class story is a reminder that apparent imperfection can carry information. A smooth, uniform modern material looks controlled. A lumpy ancient one can look crude. Yet one of those lumps may be a deliberately preserved chemical reservoir. The Romans did not need electron microscopes to understand every atom. They needed generations of observation, which mixtures heated, set quickly, survived water, and resisted damage. Practical knowledge can become sophisticated long before anyone can explain its chemistry. So, can Roman concrete heal itself? Some Roman-inspired mixtures conceal small cracks through reactions linked to lime clasts, and ancient samples preserve evidence consistent with that mechanism. That careful answer is more fascinating than the myth. It connects a white speck in a ruined wall to heat released during mixing, a crack seeking the weakest path, water carrying calcium, and crystals growing where damage began. The feature, once dismissed as sloppy workmanship, may have helped the material respond to failure. Hidden logic does not always look elegant. Sometimes it looks like a flaw, waiting 2,000 years for someone to ask why it is there.